We're back for the second video on converging functions, and now we're talking about series. So we want to talk about uniform convergence of a series. And so the real thing that we want is we're going to let our fn's be, maybe I should say fn of x, be the sum as k goes from usually 0 of a sub k, some sort of a sub k's, and then what, which is a function of x. And so we'll let f of n be some sort of series function, and then those things, that series will then converge to some function f. And we really want to ask the question is, when does this series converge uniformly? Because once it converges uniformly, then we get continuity, differentiability, integrability. We get all these things that we're really interested in. Okay, we're going to need one test to prove that uniform convergence that we really want, and it's called the Weierstrass-M test. And really all it says is that if S is a sequence of functions and mk is a sequence that converges such that the series converges, and if the absolute value of x is less than that converging sequence, then it must converge uniformly on E. And let's just remember, uniform convergence just means that it doesn't matter which x you pick, your n value suffices to prove that it's less. Okay, let's go ahead and write this proof out fairly nicely, and that is we'll let epsilon be greater than 0. And I'm gonna follow the book's proof, and so we're gonna use kind of the Cauchy way of thinking about convergence. So I'm gonna say there exists a capital N such that for all n and m greater than capital N, and we'll assume that this n is less than m. So n and m greater than capital N, that sum as k goes from n to m of m sub k is less than epsilon. So basically we're just picking capital N big enough that this sequence is always less than epsilon. Okay, so what are we going to do now? Well, now all we notice is that our function here, if we took the sum as k goes from n to m of fk of x, well, this the absolute value of this must be less than or equal to the sum as k goes from n to m of the absolute value of fk of x, which is now less than or equal to the sum as k goes from n to m of mk, and that is now, of course, less than the epsilon that we had just a second ago. So that means that these f of k's are Cauchy, which means that our fk x's, that our sum of as k goes from n to m. So it means that the sum of k's is Cauchy. So that means that this converges absolutely and uniformly. Why does it uniformly? Well, because notice the x didn't matter. The same proof works for every x that you choose. So so it converges uniformly, and it also converges absolutely. Okay, this is actually going to be really nice because the way we're going to, and by the way, this seems like a pretty straightforward thing, but what we're going to do is we're just going to create, for each function, we'll create a sequence that pairs to it. When that sequence goes to 0, then the function is going to go 0. So we'll use kind of like upper bounds in a sequence like that to make this thing go. Okay, let's talk a little bit about power series and what we mean by that. And we've heard this term before, but let's just remind ourselves what we mean by the power series. A power series is just a function written out like this. K goes from 0 to n of a sub k, x minus, and then we have some centered point to the k. So what you'll notice is we have some sort of coefficients right here, and then we have our function, x minus the center point raised to a power. And so it's a power series because it's written as a bunch of powers, right? So it's a0 plus a1 times x minus x naught plus a2 x minus x naught squared plus dot 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 dot. Okay, and so this is our power series. It's written something like that. Turns out power series are going to be really nice because they're going to kind of be the vehicle towards leading us to think about series like Taylor series and stuff converging. Power series have a radius of convergence, and well, all the radius of convergence is some r such that the following holds. Radius of r such that 1, if x minus x naught is less than r, then our power series, which the book likes to use s of x, so I'll use that. Then s of x converges absolutely. And conversely, if x minus x naught is bigger than r, then our s of x diverges. So what's the real thing going on here? Well, we're really just saying how close are we to this center point, because this x naught is the center point. We're saying when we're close, that is when we're closer than r, it converges, and when we're greater than r, it diverges. And that's all we mean by the radius of convergence. And this r is, of course, meant to be connected to the idea of the ratio test or the root test. And that's going to let us know that it converges on one side and diverges on the other side. And then what happens on the boundaries, we don't know. We're unsure about. Okay. So our main theorem says this about convergence. And this is 7.21. And the description of this theorem is really quite intense. So I'm not sure I'm going to go through all the details of writing it down. But basically it says if s of x is our power series, so if it's a power series centered at x naught, and we're going to let r be one of two things. Either we'll let r equal 1 over little r, where little r is either the lim sup as n goes to infinity of the absolute value of ak to the 1 over k. So this, if you remember, this is from the root. This is from the root test. Or little r is equal to the limit as n goes to infinity of ak plus 1 over ak. And this is from the ratio test. And it turns out you can use either one because they're both kind of doing the same thing. They were both comparing these AK values to a geometric series. So that R is that geometric series that our A's are being compared to by either the root or the ratio test. And then capital R is 1 divided by that thing. Okay, so capital R is that expression. Then what do we know? Well, then the radius of then this r is a radius of convergence, capital R, and capital R is the radius of convergence. And there's 3 important things that come from this. Number 1, the important thing is that s of x converges absolutely on this set x naught minus r, x naught plus r. So basically, within, as long as you're within the radius of convergence. And by the way, this has to be true because of the way we define the root and the ratio test. All right, so we're good with that. Number 2 says that s of x converges uniformly. And we're going to say it converges uniformly on some closed interval that's inside of that open interval. Okay, so we've got some closed interval inside that open interval, and s of x converges on that. So this is what we want. So this is what we're hoping to put a check mark in. And then finally, the last thing it says is that s of x diverges diverges for x not in that closed set. So if x is bigger than r, then it diverges. And again, it comes exactly from the root in the ratio test. So knowing the way we defined r, two of our bullets are basically instantaneous. Now there's some question of what you do if we have infinities and stuff, and the book kind of parcels that out a little bit. But what I'm really interested in converges uniformly, and see why this is important, because this means that once you know the radius of convergence, which really means once you've ran either the root test or the ratio test, then you know exactly when your function converges uniformly. And that is, it converges uniformly on any interval inside your radius. So that means that anywhere inside that radius, you can do integrals, you can do derivatives. You know your function is going to be continuous within that area. So this item number 3 is really going to be a useful one. Okay, so let's clear all this out and see if I can go about trying to prove this item number 2 for us. Okay, so item number 2, really it comes down to this. Really it comes down to this, and it's that we're going to let AB be some interval inside, and this is a closed interval, so let me write those where we can tell that it's closed. Inside my set x naught minus r and x naught plus r. Well, since it's closed, and we have this picture drawn that looks like this, and so that means x naught is right here, and then r is this distance, and so we go from there, and r is this distance, and so we go here. And then we've picked some interval inside of that, some a and b, and really all we're going to do is we just need to find it. We need to show that it's uniformly convergent, so we need some way of comparing everything in that interval to what's going on, and all we're going to do is we're just going to find some x1 value outside the interval. And because AB is closed and it's inside an open interval, then we know that's always possible. Okay, so what we're going to do is we're going to find, let x1 be an element in x naught minus r, x naught plus r, such that x minus x naught is is less than or equal to x1 minus x naught for all x in my interval AB. So not only are we going to pick a point that's outside A and B, we're going to pick a point that's further from x naught than either A or B. So we're just going to pick a point that's further away. And the real thing we want is we want this inequality. We want this x1 to be bigger than every other x. Okay. But then what I know is I know that this series with x1 must converge. I know that Sx1, which equals the sum as k goes from 1 to infinity, ak x1 minus x naught to the k converges. And so let's just call this thing right here our m. So we'll let mk equal ak x1 minus x naught to the k. And then what we'll notice is just simply notice that each point in Sx is less than that, right? And then we'll notice that AK, oh, sorry, I kind of missed a little bit here. We'll let this part be the MK. Okay. Then we'll just quickly notice that AK times x minus x naught to the k is always less than, and if let's put an absolute value on this, is always less than or equal to these mk values for all x in my AB interval. Okay, but that's great because this converges, and so now we have that Weierstrass M test. Weierstrass M test says that this thing says that the sum of AK x minus x naught to the k converges uniformly. All right, great. Well, this is great news because this means that power series converge on their radius, converge uniformly on their radius of convergence. So as long as you're within their radius of convergence, they converge uniformly, and we're in business. Let's, before I go any further, just pause and do like a calculus problem. And by the way, I'm thinking this homework is going to look a little bit more calculus-like than some of the other homeworks, but I hope that you're okay with that. Some of the proofs get a little tedious, but I really want you to kind of understand not how to do calculus problems, but how to understand why the calculus problems work the way that they work. So let's do this one. So all we have to do is we have to do something like the ratio test. And so if I do the ratio test, then my little r is going to be negative 3x plus 2 to the k plus 1 over k plus 1 times, and then I'll flip it, k over negative 3x plus 2 to the k. And then little r is, I should probably write this, is the limit as k goes to infinity of this thing. But if you notice, I get a lot of cancellation here. I get almost all of these and these cancel. And all I'm left with is 3x plus 2, negative 3x plus 2, times the limit as k goes to infinity. And we'll do absolute values here of k over k plus 1. But that's just equal to 1. So all we got was the absolute value of negative 3x plus 2. And what do we want? Well, a ratio test is where we want this to be less than 1. So the question is, when is this less than 1? Well, it's when negative 3x plus 2 is between 1 and negative 1. And so negative 3x is between, let's see, so if I subtract, I get negative 1 and negative 3. And then I divide by negative 3 and we get a positive 1 is greater than x is greater than positive 1/3. So it looks like my convergence is from here. So I can see my radius right now. My radius is my halfway point is okay. So I can see that here I have the open interval 1/3 to 1. So this is my interval x naught minus r, x naught plus r. And so what that means is that my x naught term must be the exact middle of that interval, which is 2/3, and my r must be the distance, which is 1/3. You could, if you wanted to find r, you can of course just do the two endpoints, 1 minus 1/3, and average them and divide by 2, and that works just fine. And you get 2/3 that way, or you get 1/3 that way. Okay. But regardless, this all works out. So this tells us what our radius of convergence is. This tells us that r is 1/3 and our x naught, which is the center of our interval, is 2/3. There's one lasting question which we need to ask, and that is, well, what's going on at the endpoints? So this is something that we kind of need to think about when we go through this problem, and that is what happens at both this 1/3 and 2/3. Well, let's just look really closely and see. So at x equals 1/3, what do we get? Well, we get the sum as k goes from 1 to infinity of, now if I put 1/3 in there, negative 3 times 1/3 plus 2 to the k all over k. And this is the sum as k goes from 1 to infinity of, well, this looks like a negative 1 plus 2, so it looks like 1 to the k over k. And 1 to the k is just 1, right? So this is 1 to the k. But what do we know about this? This diverges. So at x equal to 1/3, our function does not converge. Our function diverges. Okay. But what happens at x equals 1? At x equals 1, we get a lot of the same things. Let me cut straight to the end here. So we put a positive 1 in, and we get negative 1 to the k over k as k goes from, oh, I guess we're going 0. No, as k goes from 1 to infinity. And what is that? Well, now that converges by the alternating series test. So what this means is that our interval, and what we call the interval of convergence, which you'll recall that from calculus class. So we have our interval of convergence. And what our interval of convergence is, well, it starts at 1/3 and ends at 1. 1 is included in the interval, and 1/3 is not included in the interval. So notice the endpoints, the 1 and the 1/3, they could be included in the convergence, or they could not be included in the convergence. And so you have to kind of think your way through each point to determine whether they're included or not. A few other things. It's also definitely possible for your radius of convergence to be 0, and that is for your function to only converge at one point, which is the center. It's also possible for your radius of convergence to be infinity, and that is it converges from positive to negative infinity, so it converges on all real numbers. So these are all things that are very possible. Okay, just some quick observations about power series from what we just learned. So one real quick observation is that if this power series from k goes from 0 to infinity of ak x minus x naught to the k, well, what you have to notice is that this piece right here is just a polynomial. So all we have is, when we think of our partial sums are all polynomials. So we're taking a series of polynomials that converge, and so each of those polynomials are continuous, so this is continuous on that interval x naught minus r, x naught plus r. So whatever your open interval is, you get that it converges on that interval, which is great. Furthermore, it also it also is differentiable on the interval. So the next observation, and again, this all comes from uniform continuity. So furthermore, this should be differentiable. So if I call this function f of x, then is differentiable on x naught minus r, x naught plus r. But further than that, we actually know what the derivatives of polynomials are, and so we know what the derivative is going to be. The derivative is going to be the sum as k goes from 0 to infinity of ak times k x minus x naught to the k minus 1. We just use our old formulas, and it all works out just the way we expected. Okay. Finally, it also, so as a conclusion of this means that f is c infinity, that it's infinitely differentiable, because notice I can take the derivative, it's a power series, so I can do the same process. And then that's a power series, and I can do the same process. So we kind of continue the same process over and over and over and over again. And so f is continuously differentiable, infinitely differentiable. Okay. Finally, we can talk a little bit about integrals, and that is, we know that that if f of x equals the sum as k goes from 0 to infinity of ak. I should have not written this down 10 times right now, but that's okay. So if that's our power series, and it converges on, and f converges on AB, which means that it would be which means that it'd be uniformly convergent on AB, then we get that same integral result from earlier. Then the integral from a to b of f of x dx is simply the sum of those integrals of ak times the integral from a to b of, here, hold on, let's write it like this, which is the sum of the integral from a to b of ak x minus x naught to the k dx. And what's nice about that is that this is actually a formula that we should know, right? Because this formula right here just works out to use your 1 over k process, so, or your k plus 1 over k plus 1. So you can just use your antiderivative rules to make that work out. Okay, I'm going fast through these things, and by the way, there's a lot of details that I'm leaving off, so I would encourage you to go look at the book and pay kind of special attention to what are the assumptions being made, what are the intervals that we're talking about, how are they all related to each other. I don't want to bog this video down to the point that we're spending hours and hours talking about these things, but I do want you to kind of see some of the results and kind of know the results and know what we're looking at in the book. Okay, so one nice result is that we can use, once we know these things, we can actually find the closed form of some power series. So for example, here's one that was used in the book. The sum as k goes from 0 to infinity of k, x to the k, and we can turn this power series into a function. And how do we do this? Well, we know that the sum as k goes from 0 to infinity of x to the k is just 1 over 1 minus x. So all I have to do is I just have to think, how can I turn this into something that has a k on it? And if you look really close, now this is what's not obvious, but over time you start seeing this. We've got the k and then a power, so this looks like a derivative. Right? This looks like a derivative. So that means that if we took, if we had a derivative of x to the k over here, right? If we take a derivative, if we differentiate this, then that means we get the sum as k goes from 0 to infinity of k x to the k minus 1, but that means that thing has to be the derivative of 1 over 1 minus x, which we happen to know what that is. That one is 1 over 1 minus x squared. How do I do that? I put it to a negative 1 power and use the chain rule. Okay, but now I'm really close because the only difference between this and this is the fact that I have a k minus 1 and this has a k. So all I have to do is just multiply by x. And so I take this series and multiply by x times x, and what do I get? I get the sum as k goes from 0 to infinity of k x to the k, but that is equal to x over 1 minus x squared. So that series that I started with is just the series x 1 over 1 minus x squared. I messed the parentheses up there. Over 1 minus x squared. So what you can do is you can kind of start with a geometric series or something similar to it, and you can add x's to it or divide x's from it, and then take derivatives or take integrals from it to make it look like the thing that you want it to look like. And then once you do that, you know what your power series is like. There are also some other tricks that we can do. You may need to factor some numbers out or add and subtract some numbers or something to make it all work. But this is a really nice trick for turning series into functions. Okay, let's talk just a little bit about analytic functions. And what do we mean by an analytic function? And really, an analytic function is just a function that is represented by a power series. So a function is analytic. F of x is analytic on some open interval AB if if there exists a power series, by the way, we'll make sure we know that x naught is some point in AB, probably the center, right? If there exists a power series such that f of x equals the sum as k goes from 0 to infinity of ak x minus x naught to the k on some interval. Okay. On some interval CD in that's a subset of our center interval AB. I'm kind of surprised the way they worded this. Sorry, I thought they would just say that the power series was the same for all of AB. But basically, it's analytic if you can write it as a power series on some set. Now, what's interesting about this is often we have things like this. We have a situation where you have a function like, say, natural log that looks something like that, and it's analytic on some interval in here, but that interval kind of keeps going on both sides because natural log, has an asymptote. So it's only analytic on the interval, say, from 0 to 2, and then once you get outside 0 to 2, that it doesn't work out anymore. Okay, so now some of the interesting results, though, and one of these is in the book that we won't talk about, but it's called analytic continuation, and that says as long as you don't have something really bad like that asymptote, then you can extend your analytic functions out and make everything work really well. And by the way, I think that picture was probably a misleading picture, because if you think about natural log, what's going to happen is the power series is going to diverge whenever you hit that asymptote, but then will also diverge when you hit some other point in the series as well. So it won't extend to the entire function like natural log, to entire 0 to infinity like natural log does, but it will converge within some window. Okay, so this is how we think about an analytic function, and then once you have an analytic function, we can write out our Taylor expansion, and the Taylor expansion just tells us, well, what do these A of k's have to be? And the answer is we can figure this out by plugging in zeros. So you probably remember this from calculus class, but let's go back through what happened in calculus class. So if we've got f of x equals the sum as k goes from 0 to infinity of ak x minus x naught to the k. Well, the first thing you notice is what happens if you put x naught into the equation. If you put x equals x naught in the equation, well, every term becomes 0 except the very first one. So since every term becomes 0 except the first one, you're left with f of x naught is equal to just a 0. All right. Well, now the next thing we're going to do is take a derivative. And if you take a derivative, then you get the sum as k goes from 0 to infinity of a sub k, k, x minus x naught to the k minus 1. And what you'll notice now is that if you put x equal to x naught in this one, every term disappears except the a1 term. So here, f prime of x naught is going to equal a1. So it's going to equal that first term, because the 0 term became 0 because you multiplied by 0 here, and every other term becomes 0 because x minus x naught is raised to some power. Okay, let's do just a little bit more. And if I do the second derivative, I will get the sum as k goes from 0 to infinity of ak k minus 1 x minus x naught to the k minus 2. And now what you'll notice is that my second derivative at x naught, the only thing that lives now is that second term. But when I put it in, I'm going to have a 2 here. So I'm going to have 2 minus 1 times 2 times a1. So I'll get 2a1. And if I'd like, what you usually do is you usually rewrite that as that divided by 2 equals that a1 term. But let's go ahead and stick with the 2 right there for now. You keep going, and let's do the third one to make that our last one. And then we get the sum, ak, k minus 1, k minus 2, x minus x naught to the k minus 3. And what you get is that our third derivative, evaluated at x naught, is, that should have been a2, is a3, but we had to multiply a3 by 3, 2, and 1. So it's 6 a3. And you can kind of start to see the pattern, and the pattern is that in general, as we keep going through this thing, our nth derivative, evaluated at x naught, is going to be n factorial times a sub n. So importantly, we tend to write this. Importantly, we tend to write this, and this is our Taylor expansion, because we know that if the function is analytic, then these have to be the coefficients. These are the only coefficients that are possible. So if it's analytic, then we know that each an is equal to fn of x naught divided by n factorial. So our function f of x has to be represented by the series k goes from 0 to infinity of f k x0 over k factorial x minus x naught to the k. So this has to be the power series. So what's nice about that is you can now build up all of these k's. Just a note, this doesn't always work, right? So there are things that are analytic that you just can't go about, making these series because the derivatives don't work or something like that. Maybe the derivatives don't exist or something like that. But as long as this works, then this is your series, and this is what we call the Taylor expansion of the series. And you probably remember this from calculus class. Okay. I'm not going to go into great deal with all this. I'm going to let you kind of flip through the book and see the details on Taylor expansions. It's really nice to look at the remainder. We had an exercise earlier in the semester where we looked at the remainder of the Taylor polynomial, and you can bound that, and then you bound it by the size of the derivative, and then once you bound it, then you can show that that your analytic function actually has to converge. There's some common Taylor expansions that you should probably know. So you should probably know e to the x, and maybe you already do, but let me go ahead and write them out here in case you aren't aware of them. And so that is x to the k over k factorial. So that's what e to the x is. And sine of x, maybe you remember. Sine of x is the sum of negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. So sine is all of the odd terms. So we're kind of doing a similar thing to e to the x, except we're using only the odd terms and we're interlacing positive and negatives. That's because sine is an odd function, so it makes sense that we should only use the odd terms. Finally, cosine of x is the sum, as k goes from 0 to infinity, of negative 1 to the k, x to the 2k over 2k factorial. So this is almost the same as sine, except we're doing the even terms. By the way, these are all centered. All of these were centered at 0. This is what we call Maclaurin series. You probably remember that from calculus class. So Taylor, they're all called Taylor expansions. If you put it at 0, then it's called a Maclaurin expansion. But there's a really nice result. There's some nice ways we can use these series, just like we used the geometric series earlier to come up with an expansion. So let's do an example. So what if I have f of x equal to x sine of x squared? Well, it turns out that I can actually put together the sum of this pretty quickly. And one way I could do this, well, it would be to try to derive it from scratch by taking derivatives. But the easier way is just going to be to realize that, well, sine of x is over here. So my sine of x squared needs to be the sum as k goes from 0 to infinity of negative 1 to the k, x squared to the 2k plus 1 over 2k plus 1 factorial. And then if I want, I could, and then if I want, I can put that x inside. And so we get the sum as k goes from 0 to infinity of -1 to the k. And then this just becomes x to the 4k plus 2, but then we multiplied another x in, 4k plus 3 over 2k plus 1 factorial. Now what's cool is if I wanted, I could take like a derivative of this. And so the derivative, well, I could calculate the derivative by doing x sine of x squared, or I can just do the derivative over here. And it's just the sum as k goes from 0 to infinity of -1 to the k, 4k plus 3, x to the 4k plus 2, all over 2k plus 1 factorial. And so that's the derivative. You just bring down the numerator and then subtract 1. All right. Oh, I just did the problem there. All right, so here's your task. I want you to find some Taylor expansions for me. And once you find Taylor expansions, maybe using something similar to what I did just a second ago. Just put some things in, see if you can simplify them out. Don't overwork yourself. Think of this like you're back in